This is our 2024 Computational Olympiad entry. Erik, Croitoru, and Jayce Jefferson. Welcome to our project. We decided to use JavaScript and shard.js for our project. Looking at our files, we have components and constants with reusable functions that we're able to easily implement across our code. Furthermore, this saved a lot of time as we could reuse assets on the go. We did the challenge tasks and exported them onto the web page. Challenge 1. We use a simple suvat with a controlled loop. This is inefficient and this means that we miss the apogee, but it also means for larger models it is computationally inefficient. For challenge 2, we use a more precise model, and we were able to create a new graph with a fixed amount of points by finding the endpoint and segmenting the graph. Challenge 3, we considered a given point to intercept as an apogee or as a secondary point in the same curve to find the min-max values for the angle. Challenge 4, with a slightly appended formula to model 2, we were able to calculate the max range with the optimized angle. With challenge 5, this graph is essentially the amalgamation of tasks 2 through 4 with a bounding curve implemented to graphically represent the maximum limits of the graph.
This challenge mainly involved developing our own implementation of the if function available in MATLAB. While implementing challenge 7, we found something interesting with the results computed, as the 70.5 degrees curve had no maximum or minimum values plotted on it. On some debugging, we found out that this was because theta should be strictly greater than 7.5 degrees and not greater than or equal to. Challenge 8. This projectile trajectory was implemented using the whirlite method. Conditional loop is used to update the particle's position and velocity if it's not yet reached the flow. Challenge 9. This challenge builds upon the previous one. The drag whirlite function is called to compute points of the trajectory of the particle with the drag. In this model, this acceleration is also updated in each iteration based on the add resistance factor, which is computed using the calc function. Extension. Working in 3D was the most challenging yet fascinating part of the entire project. We can input the latitude and longitude of the start location of the particle. This latitude and longitude is converted into Cartesian coordinates with a bit of funny polar coordinate maths. Vectors are used to store the position, velocity, and acceleration. Initially, the velocity of the particle is set to take into account the angular speed of the Earth. Whirlite method is used to update the acceleration, which follows the inverse square law, the velocity, and the position of the particle. Finally, the trajectory is drawn using triangles and their normals. Textures and constants are changed to represent more celestial bodies. Ratios are taken based on the contents of the table shown on the screen.
We have also created a short LaTeX report that includes details about how we formatted our work and comments regarding celestial bodies. Thank you for this opportunity.